Right, so welcome to the School of Physics and Astronomy at University of Leicester. I'm Simon Vaughan. With me is Dr. Adam Povey, and the two of us are going to talk to you um, about what we do within physics, but especially the climate science and data science aspects of our school. Right, so that's us. The structure, I'm going to talk to you for about 10 minutes about how the school works, um, the makeup of our degrees, what we do in very broad terms. Then I'm going to hand over to Adam for 15 minutes to give you a very concise masterclass in an aspect of climate science and how that fits within physics. And then it'll come back to me for 15 minutes on how data science connects to physics. Right. So very quick overview of our school of physics and astronomy. I call us a medium-sized school. We take in about 110 to 130 undergraduate students per year. If you look across the UK, there's 44, 45 physics departments in the UK. We're definitely medium-sized. There are some that are 3 or 4 times larger than us and many smaller than us. Our degrees are accredited by the Institute of Physics. That's the national body that looks at standards for the discipline of physics. One thing I will say, and we'll get to this in a bit, is that for many, many years, we've had 3 kinds of degrees: physics, physics with space science, physics with astrophysics, and they are all accredited degrees and have been for many, many years. We've recently put on 2 new degrees, which hopefully are topics of interest to the people in this room here. Those are physics with climate science and physics with data science, and those are not yet accredited because they've only just started this year. I'm not remotely worried about them getting accredited in due course. It's just we need to go through an accreditation process first, and they're too new to have done that. We've actually got accreditation coming up very soon this year, so we're talking to the IAP about getting those degree courses accredited as soon as possible. An accredited degree means that once you've graduated, you can become an associate or a member of the Institute of Physics. Right. So one of the key features of our school, as well as its size, is the way that the staff and the students work together. We have a very happy family, very close and collaborative working environment between the students and the staff. So the students know us well, and the staff know the students, and this results in a very supportive atmosphere. So that as a student with us, you can get lots of help on research topics you're interested in, modules we're working through, study patterns, exam technique, etc., etc. We don't run office hours as such. We have an open door policy, so you can come and talk to us or send us a message at any time, and we'll try and respond as soon as we can. On the research side, despite being small, we punch above our weight. So physics and astronomy brings in about £14 million per year of research grant income. That's mostly won through government-funded research councils, but there's also some money from the European Space Agency and various other sources. And there's also some contracts that we do with industry, especially through our new Space Park Leicester initiative. We've got 4 research groups. They work in astrophysics, planetary science, Earth observation science, and space projects, space missions, and instrumentation. And by working with people in those areas, you'll have access to research facilities and experts in those fields. Right, so those are the areas we work in. The people and facilities we work with include all the major space agencies, all of them. High performance computers. There's a picture there of a big scary black box full of a lot of computers that lives in the physics building. That's just one of the supercomputers that we have. We also have at Leicester the director of Dirac. Dirac is a national facility built up of multiple supercomputers in universities around the country, dedicated to working on problems in particle physics, cosmology, and astrophysics. And the director of Dirac works at Leicester. One of the Dirac clusters is at Leicester. Another major facility we have at Leicester is the National Centre for Earth Observation. The Leicester is the host institute for that, and the director for that is one of our professors. It's although you may not have heard of it, you probably have heard of the British Antarctic Survey, and it sits alongside that as one of the nationally funded centres for environmental science in the UK. And part of Adam's job is actually working with NCEO. Right. So here's our degrees. They're all based around physics, but you can do physics in its freest form, just physics degree, with astrophysics, with space science, with climate science, and with data science. And there's also with a foundation year option where there's an additional year 0 at the beginning. Those all come, the first 5, all come in BSc or MPhys varieties. That means it's a 3-year degree when you finish with what's called a bachelor's degree, or a 4-year degree, which is an integrated master's. It's 1 degree all the way through, 1 graduation, 1 certificate, 1 finance arrangement. But you finish with a master's level qualification at the end. And all of those can be done with a year abroad or a year in industry. Whether that appeals actually doesn't matter now, because you can get here, you can decide what you're interested in, and you can change between them. And you can add a year in industry or a year abroad while you're here. In fact, I'd advise you to do that. Don't worry about it now. Get here, settle in, and decide whether that's interesting. And we can arrange those details during year 2. We can help you find an industry placement or another university to study at for a year. Right, how does the degree work? Obviously, I can't go through everything. I'm just going to go through the bare bones of it, but you can get an idea for years 1 to 4 here. And I've coloured in and given percentages for the number of credits you get per year for each type of module that you take. Starts off mostly core physics, some maths, some lab, a little bit of specialist material. Year 2 is similar, slightly less maths, more experimentation. In year 3, the specialist subject and the skills electives, as we call them, increase a lot. The amount of core physics goes down, and you take a research project. Then in year 4, it's mostly up to you what you study. You select from a range of specialist electives, you do a big research project, and there's the Journal of Special Topics, which is where students work together in small groups to write journal articles and edit them and review them for other teams. So there's a very structured progression from core physics and maths and an emphasis on the fundamental skills and concepts in year 1 through to a lot of independent study in year 4 and research. The topics that you'll cover are broadly similar to any Institute of Physics accredited degree: electromagnetism, optics, special relativity, nuclear and particle physics, etc. And then we've got all the electives alongside them. But as well as the material, the content, we should also really talk about the skills. This is much about the skills that you'll acquire taking a physics degree as the material that you'll be exposed to or learn about on that degree. In order to do well in a physics degree, you'll have to you'll pick up techniques and skills and get lots and lots of practice in maths, but also computing and experimental work, group work, figuring out how and when to use appropriate approximations, time management, presenting your work through posters and verbal presentations, background work, getting better at independent guided research. And then everyone will be doing that. That's just part of doing a physics degree with us. But then depending on which electives you pick, those are the courses you pick while you're here, you can also pick up projects working with industry partners in electronics, astrodynamics, teaching physics in secondary school, programming, different programming languages, etc. So there's an awful lot of skills that you will pick up and additional skills you can add to your portfolio as you're going through our degrees. A couple more things to mention. We have Space Park Leicester. This is an exciting new-ish, about 2 years old initiative in the city of Leicester, which is joint between the local authorities, international partners, and the university. And it's a big new site where university people, Adam's based there right now, and various businesses interested in space technology, use of space data, etc., all work together. What do graduates do? Physics graduates actually spoil for choice. They do all sorts of things because of all those skills I mentioned. I know physics graduates from us that have gone into meteorology or media, defense. A lot now go into data-related fields, which is why we now have a program in data science to explicitly try and support that market. Excuse me. Right, that's it for my intro part. I'm going to leave up a few questions there. We'll come back to them at the end, and some links to email, our Instagram, and our Twitter/X, whatever you want to call it, output so that you can see what we're up to. Right, hopefully that gives you a good overview of what we're doing. Now I'm going to hand over to Adam to talk for about 15 minutes about physics with climate science. So over to you, Adam. I'll stop sharing. There we go.
We will see if I can start. Are you seeing a planet?
I can see a planet.
Excellent, very good. Hello, I'm Dr. Adam Poley. I'm a lecturer here at the School of Physics, and I'm one of the scientists within the Earth observation group here. Physics is not necessarily the department people expect to find this sort of work. Often it's buried within geography or earth sciences or environmental sciences. But actually my whole background is within physics, and I thought within this talk there'll be just a little bit of trying to get across why it is physics is so fundamental to studying our planet, what its past was like, and trying to understand what the future will be like. To start off with, the degree of physics with climate science, the ideas underpinning it are trying to understand our changing climate, to give you an examination of the physical processes that govern the interactions between different parts of our planet, and actually other planets as well. The physical laws that govern the weather outside work the same on other planets. They'll just be at different temperatures or have different gases. And so we bring in some of the planetary group here at the department in Leicester, and they help us teach some parts of this course to understand those different elements, and maybe even examining exoplanets. Because climate isn't necessarily just the Earth, so my own interest and those in the Earth observation group is very much there. The idea sort of fundamentally from the degree, the selling point we're going with is try and give you the skills, the ability to understand the evidence for climate change that's in the Intergovernmental Panel for Climate Change's report. A couple of years ago, you might have heard there's this big report released by the UN about climate. They release one every 8 years or so. And that's a very dense document, but the first 100 or so pages contain what they try to make a fairly accessible introduction to what the physical basis is for climate. And the idea is within this degree, we want to take the general skills of a physics course and use those to help you understand and be able to explain to others, very important part that, what the evidence is and how it works, and also to give you the skills and experience of collecting your own data. We here at Leicester have a number of experimentalists that use instruments on the ground, instruments in aircraft, and satellite photographs, images, and other types of observations to monitor the climate we have now and to take historic data and understand and apply new techniques to that to get a new insight into what had come in the past, whilst also planning new missions going forward. And the idea within our degree is to try and bring all those different aspects together so you can better understand what the evidence is for the climate and what differences that you can make to it. For those that start the degree, though, we do admit that not everyone is going to stay interested in these things the whole time, and we appreciate that not everyone is going to end up being employed as a climate scientist. And so, as Simon was just saying, it's important to point out that the fundamentals of climate science are often things like analyzing big data sets, time series analysis, which underpins quite a lot of finance and banking in the modern day, medical statistics, overlap quite a bit with some of the statistics that we use to understand rare events or sudden shifts in a community. And as I said earlier, it's somewhat uncommon to find climate science in a physics department. That is because we're a very multidisciplinary field of we can turn up in chemistry, mathematics, engineering, geography, and those types of skills that we're hoping to teach and convey in this degree would mean that various sorts of consulting or interdisciplinary work yourself, such as charities or NGOs, would hopefully be very acceptable from someone that's done one of our degrees. So, what I want to talk about is to try and give a little taste of some of the science that's going on and give you an idea as to why we're a physics department for this type of thing. And I'm going to be using the example of global surface temperature, that measurement of the climate we all hear about most frequently of, oh, there's 1 degree of warming or 2 degree of warming or 3. Well, that number is an average of surface temperatures across the planet. Well, the surface temperature is the number we tend to report to people, partially because it's easy to measure. You can just take a thermometer and stick it in the ground and you'll measure it directly. But also the surface temperature is basically the fairest way of explaining how life experiences energy on the planet. Even though it might feel like you're feeling the air temperature outside today, the air temperature can change quite quickly. It's relatively easy to heat up and cool air. It's harder to warm up the ground and even harder to warm up the sea. And so, though there isn't as much water around Leicester as there might be at the coast, the surface temperature is often driving a lot of how you feel the energy that has been stored within our climate. We, though, can't use thermometers just to measure it everywhere. We need far too many instruments, far too much maintenance on that. So to get a view of the entire planet, we use satellites of sensors with cameras of various sorts on them, orbiting around the planet, looking everywhere all of the time in the various different ways that you can do that. But an important difference with the satellite is that it's viewing remotely. If I take a thermometer and stick it in the ground, there's a direct measurement. The heat in that ground changes the thermometer in some way. But with the satellite, we're taking an image from far, and so we're measuring remotely. Why is it that we can work out the temperature of something from orbit? Well, that's because of the thermal radiation, which you hopefully heard about. I'm guessing a lot of you have studied physics or something like it at school at the moment or in earlier years. And hopefully someone had mentioned to you that all matter that has a non-zero temperature emits radiation. Sort of matter is made up of atoms, and a simple way of explaining it. When you have temperature, that represents those atoms rattling around. And because they're moving, they emit photons. And those photons, the sorts of temperatures we tend to interact, release a thermal radiation. You might have run into the Stefan-Boltzmann law that will tell you that the amount of energy that's being released by something that has a temperature is sigma times temperature to the 4th power. And you could, in theory, set up an experiment where we measure all of the energy being emitted by something, and we could work out its temperature. But I mean, that's quite difficult. Energy is emitted in all different directions. We might not know all the different ways in which it's released. And so we wouldn't tend to try and work out temperature and that sort of thing. If we go back to a classical form of physics of 100, 150 years ago or so, there was this idea of an equipartition. In the universe, there's lots of different ways that a molecule could be rattling around within a box, such as the room I'm sat in now. And the universe has no particular preference as to which one of those modes the molecule should be in. So let's just assume that energy is equally distributed between all of these. Within this physics course, largely in the second year, we go into how you can turn that assumption and some of the basic ideas you've already picked up at A level, and then work out, well, if things can rattle around in lots of ways, and there's no preference for which one we get, Lord Rayleigh of the past, as the Rayleigh-Jeans law, derived this expression you see at the bottom, where the amount of light we see should go increase linearly with the temperature, and then should go decrease to the 4th power of the wavelength of the light we're looking at, and how much distance there is between the peaks of that wave the light is emitting. And then there's some constants that get you there. But this then created the ultraviolet catastrophe, of a very silly way for the past of wording the fact that basically if you look at smaller and smaller wavelengths, well, this number is going to get larger and larger. Now, it was that if we got down to UV light, you would start be emitting very large amounts of energy. In fact, it would be emitting infinite energy from anything that had temperature. The law works really well at long wavelengths out in the thermal and things, and that's why it was originally announced. But there was a problem at the lower wavelengths in the UV. And this was somewhere where quantum mechanics was actually a solution to the problem. Quantum mechanics told us that there's only certain discrete states that a particle could be in because the particle is itself a wave bounded in ways somewhat similar to what the light we were thinking about was. So there's not just an infinite number of possible states, there's a limitation that the universe is placed. And by rather than just equally partitioning energy between all the ways that you could rattle around this room, by using quantum mechanics to state, well, these are the partitions that you could have, you could do the thermodynamics differently, and you instead got the Planck function, which is this slightly more complicated function on the board in the middle of the slot here, where B, the amount of light we're seeing, is a bunch of constants, including H, Planck's constant, which you most frequently see in quantum mechanics, C, the speed of light, which came in from relativity and turns up all over the place in physics anyway, lambda, but now there's now to the fifth power rather than the fourth from the earlier relationship. And then there's this 1 over an exponential function that brings together everything, but also has that KB, the Boltzmann constant, which is very common to see in thermodynamics. The plot on the left-hand side is then showing in black that Rayleigh-Jean theory from earlier, where we can see the line disappearing off the top of our plot, this ultraviolet catastrophe where we couldn't capture the light that we were actually seeing. The other lines are representing, well, what light would we see from this Planck relationship for something at different temperatures? The blue line is 5,000 Kelvin, which is approximately the temperature of our sun. And you can see that the peak of that curve, the wavelengths at which the most light is being emitted, the energy is being emitted, are right in the middle of the visible radiation, which is why the light is visible. Our sun gives off a lot of light at those wavelengths, and so we evolved to see those colors. But this curve helps us not only bring together various different parts of physics, but it also helps us answer that earlier question. If I only see light, a picture of the planet, well, how can I work out what temperature it would have been? We can set a temperature within this equation, and for a given wavelength of light, it'll tell us how much light I expect to see, which means I can go the other way around. If I have a detector that rather than measuring visible light like a camera would, but I use a thermal camera, like the image here on the bottom showing the heat being emitted by a NASA scientist, I can convert how much light I saw at that one wavelength into a temperature. So I then look at some part of the UK. So I take a satellite image of some of the wavelengths. We get this beautiful color image of the country. But in the thermal wavelengths, we convert that into a temperature. We also have to apply a bunch of other corrections, the differences between different land surfaces and understanding the atmosphere in various ways. We can then form a picture like these of what the temperature of the surface is. And these examples I picked are heat waves that happened recently. If you might remember, a couple of years ago, we had a summer where it got over 40 degrees, which was entirely unreasonable for this cold, damp island. And we could use a satellite to actually monitor the changes in that temperature across the country. And so by using satellites, with the methods of physics, we can work out how to convert an image into something that people want to know, the temperature of the land. And in areas like this, you can see that the Alps in the top right are coming out in a lighter, bluer color. The Alps are quite difficult to stick lots of temperatures in. And so even if in Europe, an area where we have the money to pay for instrument campaigns, the satellites can help us track changes in temperature and, larger in this case, heat waves as they move around. We measure these types of things in a lot of different ways, and it's a particular expertise of Leicester. They were one of the first groups to exploit satellite data for this purpose, and we still lead the world in doing this. If you go to the Copernicus Climate Change Service, which is a European service providing people like the Met Office or Sainsbury's with data that they use to make decisions, the land surface temperature data in that was processed at Leicester by Leicester scientists. The history of that, the people that are teaching this degree have been doing this work for decades, though I'll admit I've not been around quite that long. Well, monitoring heat waves, looking at things, that tells us about stuff now, but there's plenty of ways of doing that. What sort of scientific questions are we looking at? Well, how are we making a difference in the world? Well, there's an idea called an urban heat island. This is the idea that cities are slightly warmer by a couple of degrees than the land around them, by the virtue of the different materials you get in the city, by using bricks and concrete and tarmac to cover over a city, you get different thermal properties than dirt. And in times like that, heat wave I showed earlier, where when temperatures get up to 40 degrees, it can be very dangerous to people, particularly those that are medically susceptible or very old or very young. Well, when the temperature outside is already 40 degrees, living within an urban area like this, when the temperature now gets enhanced by 2 or 3 degrees, makes it even more dangerous, where a circumstance of more people could die or be harmed simply because of the road that they live on. We'll use very high resolution imagery, here tens of meters at our thermal images, to make maps of the differences of temperature within, at the top, Glasgow, and at the bottom, Exeter, were two examples we used. And we then plotted those over Ordnance Survey maps. So you can see, for example, in Exeter, on the left, there's this big blue blob. Well, that's a park nearby a hospital. And that seems like the sort of thing that people would find that would cool down an area. But the buildings around that hospital are quite old, and so they absorb and retain the heat quite distinctly. And so we see that red blob around of that style of building has overwhelmed the area. Whereas on the right side, we see there's a blue area, of that's also a park, but it's surrounded in more yellowy colors. Though there's this heat island within the city, there's different magnitudes to it based on the way of building. By using our knowledge of physics to make this type of data, we can talk to councils and builders or even people living in homes to try and help them make better decisions about how we make changes to the environments they live in and how they plan things for the future, where we can build an environment that we're happier living in. And we can make people's lives better and hopefully let them live longer and less painful types of life. So that's a quick introduction to how physics helps us understand the climate and the types of things we'd be teaching you within the Physics with Climate Science course. So that's my email if anyone particularly wants to bother me in the future, and we'll have questions, I believe, at the end. Cool. So I think I should stop sharing so Simon can claim it back and tell you something about data.
Thanks, Adam. Yeah, we'll do questions at the end. Right. I'm going to go back to sharing. Right. I'm going to take a different approach to Adam here, and I'm going to focus on one very specific problem, and how aspects of data science and physics come together to help us make progress here. You'll see why I chose this one in a bit. Right. What is the connection between data science and physics? At first sight, they seem very different. One seems like it's more to do with maybe statistics or computer science, or and the other is more to do with, I don't know, magnets and lasers and planets and so on. But the two really do work together very well. So a lot of ideas from physics have carried over into data science and had a big effect, and lots of physicists have moved towards solving problems explicitly in data science that then might solve other problems in areas other than physics, and the other way around. So there's a lot of techniques from data science and new ideas coming in that really help us make progress on physics problems as well. So examples of physics ideas that have gone into data science include our understanding of entropy, and how entropy is in some sense the opposite or the negative of information. Dealing with high-dimensional spaces and how you explore them and sample them and optimize a problem in a high-dimensional space. These are problems that are actually come up in physics and have done for a long time, especially in statistical mechanics. And there are some specific physical ideas that have inspired some of the models and techniques used in data science, such as Hopfield networks, which you get a clue to the importance of the connection between physics and data science, because the Nobel Prizes for physics in 2024 went to two people who've had a big effect on deep learning. Now, how has data science impacted physics? Well, it's becoming more and more important to extract subtle signals from noisy and complicated data, sometimes using very sophisticated models. That sounds like a data science problem. But often we're interested in getting the physics out, but the how to get the physics out involves a lot of data science. And it might be detecting rare exoplanets that produce very weak signals in a huge amount of noisy data from ground-based telescopes, or it might be in-flight filtering and pre-processing of data from a camera flying on a satellite, where there's a lot of noise or cosmic rays or background, and you don't want to transmit all of that information to the ground because most of it is noise you don't need. You need some kind of inbuilt system to filter that and send cleaned data to the ground. Recovering, or the inverse problem of trying to infer atmospheric properties from satellite data. That's the kind of thing that Adam was talking about. And more generally, just discovering new subtle patterns in complex data, which could be auroral images of a gas giant planet on our solar system, or they could be medical diagnostic tests where we might be using a novel kind of camera to image people on their way through the emergency department to detect subtle changes in the radiance of their skin that might indicate early onset of different diseases. Right, so the specific problem I'm going to talk about is an astrophysics problem, and it concerns supermassive black holes. Couldn't get more physicsy than this. So a supermassive black hole is one we typically think of as between 10 to the power 5 and 10 to the power 10 solar masses. So we're talking usually millions, often billions of solar masses, or of times the mass of our sun. These live in the cores of many galaxies. And in fact, supermassive black holes probably inhabit the cores of nearly all galaxies. Often they're sat there not doing very much. A fraction, maybe 5 or 10%, depends how far back in the universe you look, of galaxies with supermassive black holes are what we call active galaxies. This is where the supermassive black hole is accreting or informally eating material from its host galaxies, drawing it in, winding it up into an accretion disk where processes a bit like friction, heat the material up until it becomes luminous. And when I say luminous, I mean emits enough radiation to outshine, in many cases, the entire galaxy of maybe 200 billion stars. So these things can be very powerful indeed. That's a good thing because it means we can see them often across across a good chunk of the universe. We can see some of these locally, and we can see very distant active galaxies. They're called quasars in that case. And in theory, these are a really great way to study physics of radiation and matter in strong gravity, where the interesting effects of the black hole change the way that light moves and matter works. The problem with all of that is that these things are very compact. So although it might have the mass of 10 million suns, it would be small enough that it would fit very neatly inside our solar system. Now, you put something that small in the center of a galaxy and park it at an average distance to a galaxy, and it's a speck, it's a dot, it's completely unresolvable with most telescopes. In fact, you would need a telescope about the size of the Earth to resolve some of these things, to actually see them as anything other than a dot in an image. Now, those of you that have been seeing the news in the past few years may know that that has been done. There is a way of combining measurements from radio telescopes across the world to produce an interference pattern that can recover an image. Now, that can only be done in a very few cases, and that's not what I'm talking about here. Instead, we're dealing with a problem. We're just accepting the fact that these things are too small to image. We can't see them so that we can understand the structure of them. We have to learn as much as we can from the light we get from this very bright dot in the middle. Now, from that light, we can either break it apart in terms of its wavelengths and study its spectrum, or we can look at how the brightness changes with time, because when we look at these things, they're sometimes brighter, sometimes fainter. Or we can look at the polarization of the light, because as it's Depending on how the light is generated and the kind of processes it goes through between emission and when it hits our telescopes, that can affect the polarization. The bit I'm going to focus on here is how it varies. So when we look at one of these AGN with the telescope, we can measure its brightness. We can come back to it a day or an hour or a year later, measure its brightness again and see how that changes with time. That's what astronomers call a light curve. And AGN happen to be very variable. They're nearly all variable. That means they fluctuate in their brightness a lot. When you plot the light curve, when you make a trace of how bright they are versus time, you get a wiggly line. Now, to a lot of people, a wiggly line is not very exciting, but to someone who studies AGN and tries to figure out how they work, this is often all we have to go on. And what those variations must be caused by is fluctuations in the accretion of matter onto the black hole. And the type of pattern of variations must be connected to the size of the accreting black hole system, and its geometry, how rapidly it's fed, how turbulence could be generated as it flows inwards. In theory, there's a lot of physics that that should be encoded in the pattern of variations we get. The trick is how to read it all off. That's what we're working on. Right. So here's what we actually get. These are observations with two different satellites. One's called XMM, and I've got the logo of it here, and one's called Swift. XMM is an European Space Agency mission, and Leicester was involved heavily in this mission. We designed some of the cameras on XMM. Similarly with Swift. Swift is a NASA-led mission with UK and Italy involvement. And again, Leicester was heavily involved in the design and build of one of the cameras. These are space missions, they're satellites. They're currently orbiting the Earth. One's in a high Earth orbit, or relatively high elliptical orbit, and one's in a low Earth orbit. Using these, they have X-ray telescopes with X-ray sensitive cameras on. We can point at my favorite AGN, if we like, and take measurements, take them over time. And what's plotted here, don't worry about the two panels. These represent two different colors of X-rays, if you like. But what's plotted here is the brightness in X-rays of one particular AGN that we've been looking at across time. And we've marked the years at the top. So you can see this is spread over more than 20 years since we started observing this. The data are spread vertically, because in a short space of time, this thing can vary a lot, go up and down a lot, but it just looks like a vertical streak because of the length of time we've put on this plot here. But the one thing you will notice from this is the data points are not exactly evenly spread. There's clumps of them. There's some years when we get lots of observations. There's some when we don't get many. There's patchy ones. If we expand out some of these regions, you can see that there's kind of semi-regular observations, and then other times there's just nothing. That's a particular problem. The methods that we use to study how things vary, most of them have been designed by economics experts or engineers, signal processing people, audio engineers. They've all been designed to work on regularly spaced data, where you get an observation every second, over and over and over again. This is the exact opposite of that. This is very, very irregular data. So we've got to adapt methods or come up with new methods to try and process and understand this. It's very much a data science problem now. We've got very patchy data. We've got data potentially from different satellites. In this case, we have 2 satellites in our test case. We've got measurement errors that mean that the variations we see when our measurement of the brightness varies, that's due to a combination of the AGN actually getting brighter or fainter and measurement errors. These things are faint. The observations are hard to make. There are significant errors on this. And sometimes those measurement errors vary in size from one observation to the next. Some observations are very precise and some relatively imprecise, and we need to account for that variation in quality as well. And then, just to make things extra complicated, what we're looking at, the natural variations of the active galaxy, that as itself a statistical process. It's not a simple curve that goes up and down, or increases or decreases in some smooth sort of pattern. It's a chaotic in an informal sense. It's a kind of chaotic, turbulent process. And the result of that is that we get lots of seemingly random variation. So we need to build a statistical model. All of those things sound like data science. Then we've got an additional problem in that the textbook methods, and there are textbook methods to handle this sort of data, they tend to be very slow. And that's quite a new problem. When I say slow, I mean they take a long time for the computer to crunch through the numbers when you're dealing with more than a few data points. So we have methods that work absolutely fine. If you've got 100 measurements, they work fine. If you've got 1,000 measurements, suddenly it's 1,000 times slower than it was with 100 points. If you've got 10,000 measurements, suddenly it's 1,000,000 times slower. That is a real problem if we want to look at lots of data. So that was our challenge. We've got very irregular data. Error bars that can be big or can be small. We need to combine observations from different telescopes with a statistical model that we're going to use to understand the data. And it needs to be computationally fast. So we needed an intersection of all those ideas in order to solve our problem. Here's what we did. And I've deliberately put an equation in here to try and scare you. It looks, probably at first sight, it looks like, oh, that's not too bad an equation. But then if you look at it a bit harder, you realize that these things are vectors and these things are matrices and all fun stuff you will learn about when you do year 1 and 2 maths with us. It's a little bit messier than it might appear at first when you understand what all the terms are. Don't worry about that. This is the bit that makes it really hard. This is the slow bit to calculate with these matrices. So we employed a trick. The kind of curve we wanted to use as the basis of our statistical model, we figured out a way to approximate the curve we wanted using simpler curves. That's what's shown in this panel on the left. And those simpler curves were chosen because they have they're amenable to certain computational tricks that we learned about by studying data science. In particular, when we put these dotted curves into this equation here, there's a very, very fast way of evaluating the function that we need. And then what we do is we add all those together to make an approximation to the curve we want. We have a fast way of computing this ugly looking function, which then allows us to make progress applying our approximated model to data, whether they've got 10 or 100 or 1,000 or 5,000 data points. And the result for that one observation I showed you is shown on the right. This is our best estimate for what's called the power spectrum, which is a bit like a measure of how the amplitude of the variations changes with different timescales. So if you wait a longer timescale, the amplitude of variation is going to grow. But the way that they grow, the envelope, if you like, of the strength of the variations is what tells you the power spectrum. And we tried some different models, but what they agree about is there's a bend in the curve at about 100 days. Or no, 100th of a day, I should say, because this is in frequency. And that's a physical timescale in the system. There's something about the variation that picks out 100th of a day as a characteristic timescale. Something's happening there, and that we've seen before in other AGN. We think is linked to the size of the black hole. If you have an AGN with 1,000,000 solar mass black hole, or a 10 million or 100 million solar mass black hole, that timescale gets slower the bigger the black hole is, and that's exactly what we'd expect because black holes scale linearly with mass. A black hole that's 10 times as massive is also 10 times as big in its radius. We'd expect the accretion disk around it to be 10 times as big. We'd expect the amount of time a variation needs to propagate across that to be 10 times slower. So measuring these timescales is really what we're trying to do with this whole project. Right, and we've made some progress on this. We used astrophysics to define what kind of model we wanted to apply to the data. We understood how our satellites work to know what the limitations of the data are. We know that traditional methods we would use on these kind of data are computationally very slow, so we can't necessarily use them. Faster methods are available, but they're very limited in how they can apply. So what we did was we built an approximation using lots and lots of faster methods, which is still fast enough. Then we applied that method with a whole bunch of other techniques to do with sampling of the data, which I'm not going to go into now, but more and more data science there, in order to recover the characteristic physical timescales in this AGN from what looks like very, very patchy data to begin with. And then the next step is to apply that to lots more AGN to study how that timescale varies with the black hole mass and other properties. That is a work in progress. Now, the reason why I chose this one is because my PhD student submitted a paper on exactly this morning. This is about as hot off the press as you can get. The press hasn't even run on this yet, because it's about to go in to be refereed. We're hoping that our fast method is useful in other areas, not just astrophysics. I can imagine some aspects of geoscience where the data are also very patchy in the way that they're sampled. And then what we're working on at the moment is applying this to lots more AGN, but there's other ways of expanding this. Now, back to you and your studies, if you're interested in physics with data science. I know I've certainly run research projects for undergraduates in areas related to this. But the key ideas, building a statistical model, the tests, a bit about time series, all of that, the fundamental ideas anyway, are covered in our new data science curriculum. And it shouldn't just be about applying those techniques to a physics problem. Those also carry over into other areas, such as finance, exploring medical data, for example. Right, I think I probably said enough on that, so I'm going to get to my last slide, which is contact details for us and some frequently asked questions about our degree. I'll leave that up there if that's useful, and then we can go to the Q&A if anyone does have any questions about anything me or Adam said.
Simon, I had a question. So you mentioned that the student submitted their PhD today. How long has their PhD taken them?
So he submitted a paper today, which is going to be a big chunk of his PhD work.
Mm-hmm.
Yeah, I didn't say that because I was a bit worried about scaring some of the people here.
Mm-hmm.
This is the result of 2 years of work so far.
Oh.
Now, it's those 2 years have also made a lot of progress on the next steps of the project. So it's not like 2 years for this bit and 2 years for the next bit and 2 years for that. Now that we're over the major hurdle of developing this method, and he's written and submitted a paper on the topic, the next step should come a lot quicker. But yeah, it was a heck of a lot of work trying this out and trying lots of dead ends to get it to work. That's normal for science.
Evan, you are free to unmute and ask your question.
Hi, can you hear me?
Hello. Yeah.
Cool. So I'm in year 12 right now, and I really want to go to Leicester to do physics. I was just wondering, do you have any advice on like how I could try and make myself stand out so I'm more likely to like get an offer?
That's a good question. So I'll be honest about the offer making process, and I think what I'm going to say applies to many, but not all universities. It's quite simple from our point of view. What we're looking for is students who have applied with all the right material and grades that are close to or better than our advertised entry grades. It's really not much more complicated than that. I know at school there's a lot of discussion about personal statements and additional stuff on your CV, and if you've got additional UCAS points from extracurricular activities and so on, all of that stuff's great. But I would say that is that becomes important if you're close to a borderline. If you're doing the right subjects, namely physics and maths and something else, and your grades are what we're asking for, or your predicted grades are what we're asking for, then just apply. It's that simple. All the effort into the personal statement and all that other stuff is comes in useful if it turns out that your actual grades on the day are not quite as good as expected. And then what we have to do is we have to rank the people that are near misses. And we do that by close inspection of which subjects they studied, what grades they got on an individual basis, personal statement, additional UCAS points, and all that kind of stuff. But if you're in year 12, the main thing to do is if you haven't already done it, go to some open days and just find out what these places are like. Not just Leicester, but other places. Other physics departments are available, and then apply as soon as you can. You get 5 applications, don't you, with UCAS?
Yep. We've had another question in the chat. So question is, for students taking the main physics course, are there still opportunities to take modules about data science and climate science if you're not sure if you want to specialize yet?
Absolutely. So I skipped very quickly over this at the beginning, but our degree programs are designed with as much flexibility as we could put in them. So in year 1, you'll pick 3 very short courses out of 4 from the specialism. So astrophysics, space science, data science, climate science. You'll do 3 of them. And then in year 2, you'll do 2 of those. And then in year 3, it becomes a bit more specialized. So if you're on the straight physics course, absolutely, you can do astrophysics and climate science and data science in year 1. You can do that as a combination because you're not sure which of them you're more interested in. That's absolutely fine. And we've tried to deliberately design year 1 and 2. So there's a lot of, you have a lot of ability to try before you buy, to just try small amounts of these different subjects, find out if you're interested, and not get forced down one road because of a decision that you made earlier on. So if you've taken data science and you found it interesting, you can then swap to the physics with data science degree in year 1 or 2 or 3, as long as you've taken that subject earlier. There's a question in the chat: how do we compare to other physics departments? Too many different variables to talk about there. So size-wise and medium size, in terms of research grant income, we do very well. 14 million is quite a lot for a department of our size. Our specialist areas are astrophysics, space science, Earth observation science, and space instrumentation. So that's one thing that does vary from one physics department to another, is they will all have will have strong research groups in different areas. Some might be very interested in laser physics or radio astronomy or nuclear physics or semiconductors. For us, it's those 4 subjects I named before. So that's one thing that is quite different from one to the next. Another thing that will change is the kind of culture, the attitude, the way that the students interact with the staff. That could be very different. Like I say, at Leicester, we try to take a very relaxed, try and build a very friendly environment, so students are quite happy to come and talk to us when they get stuck, because or when they're interested in a topic, because talking through problems earlier tends to help rather than saving them up till the day before the exam, and then it's very hard to provide any help. And that can be different from one department to the next. Some departments I know operate an office hours policy, when you're allowed to go and talk to your lecturer or professor, 2 till 5 on a Tuesday or something like that. We don't have anything like that. If people are in and available, you should be able to go and talk to them. Well, if you do think of anything later, do feel free to email physug, physics undergraduate, at le.ac.uk. And you can follow what we get up to through Twitter, X, whatever you want to call it, and Instagram. There's the handles and tags and whatnot up there for you to follow.